All right, welcome to our last video, as I take a deep breath. This last video is for 3.5 dimensions of four subspaces, and really kind of highlighting one of the applications for not just the four subspaces, but I think making a connection to graph theory, which then connects to many applications outside of this, and just kind of shows you, I think, the connections that linear algebra has, that as we've been working through all of this and looking at the textbook, and the stuff isn't crazy challenging procedurally, and conceptually even it can be advanced, but where this stuff might be used and how it's applied, why even talk about it, questions that should always be asked, we can kind of start to see some applications here. And especially in my studies of graph theory and looking at discrete mathematics and how AI and machine learning, all of this is based off of directed graphs. You can kind of see how this can be translated into a matrix very quickly. Algebraic coding theory, all of that with the Artemis spaceship and transferring data. So all of that can be boiled down to a lot of graph theory, which can be translated into matrices, and then we can identify the spaces. And so that's what I want to do. I'm going to kind of walk through the example that he gives on where he mentions Kirchhoff's law, the current law, and talking about voltages. And I'm not going to dive super deep. I mean, confession, again, studied and did masters in applied mathematics. I am not a master of knowledge in Kirchhoff's law and electrical engineering, nor a lot of specific engineering. And so I'm not going to dive super deep into that. I really just want to identify this problem and this kind of word problem application, work through the spaces, but really, just like he does in the book, when he gets into the row space and the left null space, is just to identify how we can answer those questions looking at the graph, looking at the matrix, seeing how all the dimension rules apply, but then again, how this kind of beautiful picture forms in general language that can then be applied to everything. And so that's my plan. My watch just beeped, so I don't know if it's still filming, so I'm gonna check. All right, so hopefully the audio is still picking up, so I apologize about that. And so that's the purpose of this video. So I won't dig into the law, essentially the laws that he gives at the bottom of page 135. I'm going to leave that for you to kind of take a look at. But I do want to look at this matrix because, again, I think it gives just another example of how to identify the spaces. And so what's first pictured is this is a graph. Depending on your background, you may be used to seeing graphs in terms of functions and coordinates and coordinate geometry. We can also define a graph by a set of vertices or nodes and edges that connect those nodes. And many different graphs can be formed. If you hopefully get the chance to take a graph theory course or a discrete mathematics course, you'll see these because this, I don't know when graph theory started. I want to say it's fairly newer, but that's really based on not a lot of knowledge of math history to this point right now. But the idea is that I can take a look at this graph and I can connect this graph to the equation AX is equal to B. B represents what's referred to as edges, and then my X's are my nodes. They're my vertices, they're my endpoints. And what I actually want to create is what's referred to as an incidence matrix. And the purpose of the incidence matrix is it tells which two nodes are connected, which two vertices are connected, and then directionally, how are they connected. And again, the application specifically is around voltage and nodes and electrical wires. So sending signal and accounting voltage at each node. And so when I'm looking at this, if I think about X1 being my very first column, B1 would be a negative direction from X1, a positive direction to X2. So again, if I'm thinking about my columns as X1, X2, X3, X4, and that's it, I would have negative 1, 1, and then zeros for these other nodes. There's no current or voltage flowing in that first one. My B2 edge would again be a negative 1 for X1, but a positive 1 for X3. So I would have a matrix that would look like this. B3 would be negative 1 in my X2, positive 1 in my X3. So 0, negative 1, 1, 0. My B4 a negative 1 in x2, but a positive 1 in x4. So 0, negative 1, 0, 1. And I thought I might run out of space, so I'm going to write this one more time. Where for B5, I've got negative 1 from x3, positive 1 for x4. So 0, 0, negative 1, 1. And again, this corresponds, just double checking, but corresponds to the instance matrix that you'll see in the textbook. He does not list the zeros. It's kind of common practice. When your matrix has a lot of zeros in it, you don't write them. We just fill in the numbers that are not zero. But this would reference my incidence. And so if I was to multiply it by x1, x2, x3, x4, my nodes, we essentially create the edges, b1, b2, b3, b4, b5, and thus my equation ax is equal to b. But because we have this matrix, we can now kind of apply our knowledge of spaces so far and identifying the dimensions and taking a look at that process. And so we're going to start with looking at the null space of my matrix A, which is my instance matrix here. And remember, for the null space, we are looking, I was kind of thinking of column space a second ago, but I'm looking at the solutions to when this is set equal to 0. And so if I was to go through and essentially augment this with zeros, I want to find the solutions to this. Well, let's just kind of go equation by equation, much like we did in this unit. And the first equation would be negative x1 plus x2 is equal to 0. So if I'm just taking the first line. And so if I solve this, notice we get that x2 is equal to x1. If I look at the second line, we get negative x1 plus x3 equals 0. Well, that implies that x3 is equal to x1. If I go down to my third equation, we get that negative x2 plus x3 is equal to 0. So x3 equals x2, which makes sense. Both of these are the same. When I look at the third equation, we get negative x2 plus x4 is equal to 0. And that implies that x4 is equal to x2. And so x4 equals x2, x3 equals x2, and in theory x1 equals x2. In other words, they're all equal to each other. And so my null space consists of only one, or not null space, consists of one vector. The basis for the null space consists of one vector. I'm trying to be really careful with my words. The only solution would essentially be the vector where C, 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 C. They just all have to be the same constant, and this would solve it. And you can kind of see that, because if I multiply this by the same scalar and add 0, same scalar, add 0, same scalar, add 0, same scalar, add 0. But what I now have is a basis for the null space. For my matrix A, the dimension of this would be 1. That would be the dimension of the null space. And remember that the null space, it works in Rn. And so if I take this and I subtract it from 4, since I have 4 columns, that tells me what the rank of this matrix has to be without actually having to go through and put this into reduced row echelon form or find its column space. We can identify the dimension for this, and in theory the row space immediately now. So the null space had a dimension of 1. That means the rank, which is the dimension of the column space, has to be 3. And so moving into column space now, we've got my basis for the null space. The column space, the rank is 3, so I know the dimension, the number of vectors that form the basis for the column space. If I'm looking at the original, there has to be 3 vectors that work there, 3 columns. Well, we only have 4 columns. And so we have 2 methods to dig into this, and he kind of shows it in the book and talks about it in the book, and I'm just going to kind of talk out loud. You can put this into reduced row echelon form. We can also use our technique from the first unit, and that's the one that I'm going to use right now. That if I start comparing columns together, taking the first column to be independent, looking at the second column, there's no scalar multiple, so these 2 are independent. And then looking at the third one, notice because these are zeros, there's no way to get this entry. The first 3 columns are linearly independent of each other. And so my column space is created by these 3 vectors, or spanned by these 3 vectors. 0, 0, 1, 0, negative 1, negative 1, 0. And then 0, 1, 1, 0, negative 1. And notice this basis would have a dimension of 3. The space has 3 vectors in its basis. So again, the dimension, the rank working out here. Null space solution would be -1, -1, -1, -1. Really 1, 1, 1, 1, 1. Really any scalar as long as it's the same. But we get our column space from here, which is our rank. And if I take that then, we know that the row space has to have the same rank. This is where things get a little interesting and we start getting into more of the application piece. Drawing the connection between this and the picture that we have. And so what I'm going to do is kind of go back to listing out the B1, B2, B3, B4, B5. I'm going to erase this. Just remember how it was columns 1, 2, and 3. The row space, which is the column space of A transpose, should have a dimension of 3. So when I'm looking at my rows here, we have a total of 5 rows. There should be 3 rows that are linearly independent. And right off the bat, and it highlights it in the book, so there's really not a giveaway here, but when I'm looking at the first 3 rows, this third row is a linear combination of the first 2. So unlike with the column, so I can take the first 3 columns to form the basis for the column space. To form the basis of the row space, I can't take the first 3. I'm going to take the first 2 because of the 0 and the 1, and the 4th. So I'm going to take 1, 2, and 4. We'll take those rows. And that's what's going to form the basis for the row space. One of the ways to kind of see how this is dependent is that I can take this and do 1 minus the other, row 2 minus row 3, and that would form row 3. So row 2 minus row 1, excuse me, I think I said row 3. So row 2 minus row 1 gives me row 3. So this is a linear combination of the previous 2. But again, there's no way to create a 1 here from these because of the zeros. One of the fastest ways, I think, to kind of see it right off the bat. And when I'm looking at that then, if I take a look at these 3 edges, 1, 2, and 4, I want you to notice that if I follow that, 1, 2, and 4, they don't loop on themselves at all. In other words, we call this a tree. So if I take edges 1, 2, and 4, they don't connect to form a loop, essentially a circuit. They stay disconnected. And so what's kind of interesting with that is if we took the same approach, we could argue 1, 2, and 5 also form another tree. And if I was to take the rows 1, 2, and 5, that would also form a basis for the row space. Because again, notice that if I disregard this one, there's no way to create that entry as well from the previous one. So we took the first 3 independent rows, but it's possible to take this one as well. 1, 2, and 5. And notice each time that creates this. And so we've got a rank of 3 for the dimension of the row space, equal to the dimension of the row space there. But just kind of pictorially, just kind of noticing that. Now if we went back to the column space, remember that the column space took these 3 columns. And if I focus on looking at x1, x2, and x3, that would form a loop. And I believe it even looks specifically at the edges 1, 2, and 3. This would essentially create a loop. And if you remember, 1, 2, and 3 were linearly dependent in terms of the rows. And so notice how there are 2 rows. If I take these first 3 to be my row space, the basis of my row space, then these 2 vectors are linearly dependent on that. That creates the dimension for the left null space, being 2. In other words, it's kind of showing us that if I have something that creates a loop, then that is part of the basis of my left null space. You know, this contains all the loops. So 1, 2, and 3 form a loop, but so do 3, 4, and 5. Every other loop that could be made after that would be a combination of those 2. It's contained within that basis. And so I have a dimension of 2. There are 2 sets of edges that form loops. In other words, it seems like the space that gets created here in this left null space is helping picture where there are loops, and the column space is dictating essentially where there are trees. And again, he kind of talks about this in terms of Kirchhoff's voltage law and Kirchhoff's law. that by the time we got even into the left null space conversation, I didn't find it. We could have taken this matrix and transposed it, put it in a reduced echelon form to identify the basis and the dimension, but we've actually identified it just from the graph theory. Noticing the connection between the loops and the solutions we had when we first found the row space. And this could, in theory, be applied to any application. This concept of trees and loops is independent of necessarily thinking about this as electrical engineering. And so really just the takeaway I want you to have is just how we can label this based off of the word problem. I was telling AP Cal class that when we're studying optimization, the procedure is really the same for every single problem. Just how it's dressed is what's different. And as long as we can read through a different scenario but walk through the same process, it's solvable in a very similar way. And we do that here. This could be describing maybe not voltage and currents, but maybe it's a directed path in terms of AI and machine learning. Maybe it's a directed path like the bridge problem. And I can't think of the beginning of it, but it's a famous bridge problem about trying to reach every single island. And if we draw out and create an incidence matrix, we can look at the dimensions of the 4 subspaces and how they might connect and help describe that problem. And so it's just kind of where linear algebra is kind of sitting behind the curtain, Wizard of Oz style, manipulating and helping represent visually solutions to these problems. And so there's many applications that can be solved within graph theory and within linear algebra. It's kind of that ground layer underneath. So hopefully this kind of helps a little bit. I know a little shaky in terms of the application, especially in digging into the spaces. So as I learn more, I'll come back and kind of refilm and update. But if you have any questions on this, please let me know. You'll essentially see a question on Kirchhoff's law and incidence matrices in terms of your problem set. So I wanted to make sure that we at least discussed this so you'd have something to go back and look at. But again, let me know if you have any questions. Thank you.